Yeah, so hello everyone. This is the advanced section in the mini course of computation. And today we're going to have Kartikeya to talk about quantum computing from a more condensed matter perspective. And Kartikeya, maybe you can first introduce yourself and then start the talk.
Yeah, sure. So, hello everyone. My name is Kartikeya Arora, and I'm a junior undergraduate pursuing engineering physics. Today I'll be talking about quantum computing, but through a condensed matter perspective. Before we begin, I'd like to point out that if anyone has some questions in between, you're free to unmute yourself and stop in between, or post your questions in the comment box if you may. So I'll begin now. So in this lecture presentation, we'll be basically first revising quantum mechanics, and then we'll continue into what condensed matter physics is, and especially many-body physics. Then we'll briefly go through the basics of exact diagonalizations, DMRG, and tensor networks. These are basically the techniques which are prevalent in condensed matter physics to solve models, and all this will be paving our way for quantum computing and quantum simulation studies to follow. So to begin with, as many of you might know, quantum mechanics is a fundamental theory in physics that helps to understand nature at the level of subatomic particles. Now, quantum mechanics is peculiar in the sense that it has two interesting properties. First is the superposition, which is the ability of a quantum state to be in multiple states at a time until it is measured. So many of you might know the famous Schrödinger's cat experiment, that cat is assumed to be both dead and alive until we observe it. That is basically the superposition principle. And the other one is quantum entanglement. It is a strong quantum correlation between two entangled particles, in the sense that if they are entangled, we can describe a state such that if we know the properties or measurement of one of the particles, we inevitably know about the other. So moving on, here I would like to first point out what a wave function is. I have been told that wave function seems to be daunting at first to people who haven't been introduced to quantum physics in a pedagogical way. So so wave function basically roots itself from a basic property known as wave-particle duality. Now, what wave-particle duality is that any matter, be it electrons, photons, or things like that, possess both particles and wave-like characteristics. Now, what it means is that an electron, for example, is not a wave, but it's a point charge whose behavior in some sense can be described by functions that are usually used to describe waves. And these functions itself are called wave functions, which are used to study the Schrödinger equation, which we'll study in the next coming slides. And these wave functions basically represent the likelihood of the particle being at a certain position in space at a particular time. Specifically, the square of the magnitude of the wave function gives us the probability density. That is the probability per volume that we will find the particle at a location in space. Now, the equation below basically represents the sum of the probabilities of finding the particle at each position in space, and obviously it should be 1 because the particle is bound to be somewhere. Right? So moving on, analogous to the Newton's laws in classical mechanics or the Maxwell's equation in electrodynamics, we have the Schrödinger equation in quantum mechanics, which is a linear partial differential equation that governs the wave functions of the quantum mechanical system. Now, these two forms are quite similar and interchangeable. The form on the left-hand side is used when we use the wave picture of the quantum mechanics, and the one on the right-hand side is used when we use Dirac notation. Now, we'll mainly focus on the form of the equation on the right-hand side. H operator here is the Hamiltonian operator, which basically describes the total energy of the system. Now, it works in a way that if we have a wave function denoted here by psi, and we apply the Hamiltonian operator on it, we get the energy eigenvalue and the psi, the wave function back. Now, this is similar to what we call eigenvalues and eigenvectors. For those of you who don't know, an eigenvalue or an eigenvector is such that, let's say we have a vector v, and we act an operator a on it. If we get the result in the form of lambda v, such that v is the same eigenvector and lambda is some number, lambda and a are respectively the eigenvalues and eigenvectors of the state v. In simpler terms, we can understand it like this, that eigenvalues and eigenvectors corresponds to the measurement results in experiments. For example, the ground state of a particular system will be the eigenvector corresponding to the lowest eigenvalue of the Hamiltonian, because the lowest eigenvalue of the Hamiltonian being the least, having the least value is the state which has the lowest energy, and hence is the ground state of the system. So any questions till now? If not, then we'll continue. So we now come to what condensed matter physics is. So condensed matter physics is a field of physics that deals with microscopic and microscopic physical properties of matter, especially the solid and liquid phases, hence the name condensed, which arise from electromagnetic forces between atoms, right? And a subset of that is called many-body physics. Many-body physics or many-body theory is an area of physics that provides the framework for understanding a collective behavior of a large number of interacting particles. It basically aims to understand how the interaction between particles change the dynamics of the system with time. So in many-body physics, there are basically two types of models that we study, known as spin models and second quantization models. And they look something like this. But the main point here is that they are interconvertible using something called as Jordan-Wigner transformation. So they represent the same things, but in a different picture. And in this presentation, we'll be mainly focusing on spin models only. So to understand what spin models are, a quantum spin model is a quantum Hamiltonian that describes a system which consists of spins. We can visualize it as follows. We can assume that there is a lattice with magnetic dipoles at each point in space. And what we are basically trying to understand is that how these dipoles interact with each other and act in the presence of an external magnetic fields, let's say. So this is the main reason we study spin models or the quantum Hamiltonians of it. To understand
sorry, Kartikeya, maybe
what
let
spin
me
models basically are, we'll basically
Kartikeya?
yeah.
Oh, I just want to ask a clarification questions from the previous slides.
Yeah.
Yeah, so just to make sure, so it's like each dot on this ring, I should think of it as like a particle.
Like a magnetic dipole.
A dipole. So it's like an abstract model, but I see. But in reality, we might be thinking of it as a I don't know.
So it basically we can, the thing that happens in reality is that there is a particle at each lattice point, and each particle has something called a quantum spin, which can be thought of it as a magnetic dipole. So what we are trying to understand is that how these dipoles are interacting with each other and how they're interacting with an external field.
I see. Okay, thank you.
Okay, so moving ahead. So now we can see this is one of the famous models known as the Heisenberg spin chain. We'll try to see what the various components of this equation are. So of course, the left-hand side represents the Hamiltonian or the total energy of the system. J here represents the coupling constant or the interaction energy. As we can see here that the subscript is J plus 1. So there is a nearest neighbor interaction. And the interaction energy between them is described by this coupling constant J. The H here is the external magnetic field. And the sigma J is the response to the external magnetic field, if you say. And these Pauli matrices, sigma X, sigma Y, and sigma Z, they combine to form these sigma J and sigma J plus 1, things like that. So to understand better, if we have periodic boundary conditions, let's say the sigma n plus 1 and sigma 1 will be the same. And we'll have a circular lattice, each point having magnetic dipoles, as I just said, and they'll be interacting with each other, specifically to their nearest neighbors and to the external magnetic field. Now, many of you might wonder, what is the role of spin? Like it's a quantum thing, and how does what role does it play in our daily lives, or how does it help in making technology better? So in recent times, there has been an emerging field known as spintronics, which is an amalgamation of quantum spin and electronics. And one of the most famous application of it is the spin transistor, which operates on electron spin and embodying it as a two-state quantum system, because a spin can be either up or down. So it represents a simple two-state quantum system. And unlike the classical transistor, which operates on electric current, it operates on a more fundamental level. And using that, we have been able to make a better non-volatile solid state storage, and known as magnetic random access memory, which is both faster and semi-permanent and more sustainable compared to the versions which we are using now. To move ahead, now we'll be learning about how to solve these models. Like we have seen different types of models till now, the spin models or the second quantization models. So for now, solving the model basically boils down to calculating the eigenvalues or the energy levels and eigenstates or the energy states of the Hamiltonian operator of the system. So we remember that the Schrödinger equation that says if we apply the Hamiltonian operator to a wave function, we get the energy eigenvalue and the wave function back. So now the most intuitive answer here would be that we form the Hamiltonian matrix using the algorithm or the procedure that I just showed, using those Pauli matrices and Kronecker product and things like that, and calculate its eigenvalues and eigenvectors using our favorite linear algebra library. For example, NumPy or SciPy for those of you who use Python. And this is correct. And this method of solving the model is known as exact diagonalization. Now, this looks good, but there is a limitation to this. The Hilbert space or the dimension of the Hamiltonian matrix, if you may, grows as 2 raised to the power n, where n is the number of spins or the system size. Now, it turns out that only for 40 particles, we need around 8 TB of memory to store the information of the ground state only. And for 300 particles, the number of the basis states or the number of vectors that we need to solve is already exceed the number of atoms in the universe. So this procedure or algorithm limits us to only small system sizes. So we need another way around it. So before we cover that, are there any questions still here?
Yeah, I do have some questions if people don't have.
Yeah.
So can you go back like maybe 2-3 slides? Yeah. Maybe one more when you talk about the why this can be helpful. Yeah, here. Can you roughly explain the last paragraph again?
Okay. Now, the spin transistor that we create here, it works differently than the classical transistors. In spin transistor, we basically use the property of quantum spins instead of the electronics that we originally use, because spin transistor also behaves like a two-state quantum system. A spin can be either up or down, right? And instead of being operating on current, like the original classical transistor, it operates at a more fundamental level on the spins of the electrons. So we don't need to pass current through it every time when we need to make some measurement or perform some calculations. And because of that, it doesn't heat, and it creates a semi-permanent form of memory, just like the RAMs we have in our computers. And because of not using current, it is more sustainable. And because it can persist infinitely, it can be used to create a cost-effective, non-volatile solid-state storage.
I see. But probably everything should be in very low temperature. That's probably the main caveat.
Yes. That's a limitation for now. Yeah.
I see. But ideally, then you will have all the other advantage.
Yes.
Okay, great. Thank you.
So, any further questions still here? If not, then I'll proceed. So what next? One of the possible solutions is that now we know that from condensed matter physics that most of the properties of the system can be studied by only the ground state of the system. It has been observed in condensed matter physics that all of the properties of the system, let's say the first excited or second excited state, they can also be extrapolated if we know the ground state of the system. So if we focus on that only in this spirit, we can see that if we calculate the eigenvalues or eigenvectors of the Hamiltonian, we see that most of the information is concentrated only in the initial states of the system, for example, only up to a few excited states. So a reasonable thing here would be to perform a change of basis, or classically, if you like to vision it, it would be the rotation of coordinate axis, such that all of the information is limited only to, say, 10 states of the system. And then what we do is truncate the rest of the states we don't need and use that. So what we'll be having here is that, for example, if we originally had 100 states that we need to consider, now we'll only be considering only 10 states. So this helps to solve the dimensionality issue. And this form of algorithm is called numerical renormalization group. But the problem with this is that it works for Kondo and Anderson impurity problems, but doesn't work well with strongly correlated systems like the Heisenberg chain we just saw. The reason for that is that this algorithm is not basically able to incorporate or preserve the interaction picture as well. And hence the strongly correlated systems where interactions play a major role, this algorithm doesn't work well. So we use something called the density matrix renormalization group, or DMRG. Now, DMRG was invented by Steve White in 1992. It is an efficient method for 1D systems. It's a variational algorithm that helps to find the lowest energy eigenstate of the Hamiltonian in the form of a matrix product state. Now, there are two ways to study density DMRG. One is the traditional route that Steve White used and which evolved into the matrix product state formulation of this algorithm. But we don't have much time, so we'll dive directly into the MPS form of the DMRG. MPS here is matrix product states. But before that, we'll revise what basics of what tensors and tensor networks are. So for our purposes, a tensor can be simply understood as a multidimensional array of numbers, and we use diagrammatic notations to simplify it. Now, the number of legs here represent the rank of the tensor. For example, a vector having rank 1 has one leg only here. And a B is a matrix, so it has two legs. And because we need to index to pinpoint to any element of the tensor, and similarly 3 or 4 for higher end tensors. And we can also perform other linear algebra operations like contraction over an index. For example, the example on the left-hand side basically represents matrix multiplication, and it can be visualized and solved easily using these notations. So to summarize, it is tensor networks or tensors are basically a diagrammatic way to simplify complex linear algebra calculations. Now we come back to DMRG. Now to convey what the bigger picture of DMRG algorithm is, it is useful to summarize it diagrammatically instead of going into details. So what's happening here is that the gray dots that you see, the tensor network in the middle, is the Hamiltonian of the system. This tensor network represents the Hamiltonian of the system. And these yellow and pink purple boxes, these basically represents the bonds and the interaction between the system. The blue dot here is our initial guess. It is an initial random guess for the ground state of the system. Now, what we are basically trying to do is, we are trying to incorporate all the physical properties of these bonds, of the interactions, and the physical properties of the system into this initial guess to formulate it into the optimized ground state of the system. So it is basically a variational optimization algorithm. For those of you who might be interested about the computational complexity of this, might also see the Davidson or see that we basically use Davidson or Langso's algorithm as an eigensolver here. But the most costly step here is the multiplication only. After that, after the bond tensor.
Sorry to interrupt.
Yeah.
Can you explain again how does ground state like correspond in this picture?
Okay, so what we are basically doing is we have an initial guess here, and what we try to do is that we try to contract once.
Guess for the ground state, or what do you mean by initial guess?
We take any random matrix product state only.
Okay, so
depending on the
system
properties of the system. Yeah, it is a guess for ground state. Based on like other systems that we might have seen that are similar to this. And then we try to contract it one side at a time with other bonds. And when they are contracted together, we transform the basis and we basically try to optimize it till we have an optimized ground state for ourselves.
Optimal.
Does this make sense?
Yeah,
optimizing the sense. Yeah. So what we basically do is that let's say in the first step we have contracted these two sides, and we continue this similar behavior for all the other sides till we have an initial wave function. This wave functions almost always is the optimized ground state for us. So, okay. And after this, we basically repeat this procedure over all the bonds. Like here we started at this side. In the next step, we start at this side and continue to do this. So after all these sweeps, this process is basically known as a sweep. After all these sweeps, we obtain an optimized ground state for a system. Does this make sense?
Is this like theoretically proved that you can always get like optimal ground state, or?
Yeah, like actually, it is proved using a quantum information perspective, but I thought it would be possible to cover that much here. So
I see.
I didn't actually.
Maybe you can provide some reference. Yeah.
Yeah, sure.
Thanks.
Shall I continue? If you don't have.
Yeah, sure. Thanks.
Yeah, okay. So yeah, so this process is repeated over all the bonds, and we get our optimized ground state. For those of you who couldn't follow, here's a summary. Tensors are mathematical structures that help to visualize and simplify complex linear algebra calculations. In this tensor network, the middle one basically represents the Hamiltonian of the system, and the purple and these yellow boxes represent the bonds. And DMRG is basically an optimization algorithm that helps us to find the ground state of a large system. So, any questions? If not, then I'll continue. So we move forward to the later part, the second part of the talk, which is quantum computing. Now, quantum computing is a type of computation that harnesses the properties of quantum states, such as superposition, interference, entanglement, etc., to perform calculations. Now, one of the questions would be why quantum computers are an optimal platform for condensed matter physics research. And the answer was given by Feynman that nature, in fact, is quantum in nature, right? And to make a better simulation of it, it only makes sense to perform our calculations or to simulate it on a quantum platform. Now, matter's constituent particles like electrons or quarks, etc., they interact with each other to give rise to exotic properties like superconductivity or ferromagnetism. And the condensed matter physicist's job is to basically understand how these particles interaction give rise to these interesting behaviors. And how does the laws of quantum mechanics govern these systems and the dynamics with time. This was basically the motivation for building and simulating condensed matter systems or models on a quantum computer. Now, as a time example, I'll discuss the application of a language called Qiskit. It is an quantum programming language developed by IBM. I'd discuss how to simulate a discrete time crystal using Qiskit on an IBM supercomputer. So before that, time crystals were originally conceived by a Nobel laureate Frank Wilczek as a temporal analog to the familiar phenomena of space crystals, for example, diamonds or quartz. For those of you who don't know, an ordinary crystal is a spatial crystal is basically a spatial organization of atoms in a periodic way on a lattice. It forms a stable periodic structure in space. Now, the time crystals are basically the temporal analog of these space crystals. Now, in the language of theoretical physics, there is something known as space translational symmetry, which basically says that if I perform an experiment here or somewhere or someplace 100 kilometers away from here, given that the environmental conditions are the same, I expect to get the same results, and that makes sense. But in some systems, especially crystals, this space translational symmetry does not hold true every time. Right now, let's consider a particle, a free particle in space. We can do some experiments on this particle at a position here or somewhere in between these two places also, and we expect to get the same results. But in crystals, what happens is that these particles obey the laws of physics in a sense that they obey Schrödinger's equation at only certain points in space, and that point being the lattice points of the crystal, and not in between those. For example, the particle won't obey the laws of the model that we are studying at a point, at some point between the space of the cube. Okay, and so in some sense, it is less symmetrical than a free particle in a continuous space. So this phenomena is known as spontaneously breaking of space translational symmetry. Now, time crystals theoretically were proposed to break similarly time translational symmetry, which says that if I perform an experiment now or 10 days later, I expect to get the same results given the environmental conditions are same. But it was found out that it is impossible to break continuous time translational symmetry in thermal equilibrium. time, it appeared that it didn't break symmetries just like space, and it defied our desire for a complete space-time unity. But later it was found out that in certain systems, especially systems known as Floquet systems, which stably oscillate in time in a periodic fashion, and are many body localized, this physics term, condensed matter physics term, they obey the discrete time translational symmetry and helps to break it, essentially make a discrete time crystal out of it. So I won't go into details of what many body localization or Floquet systems are, and I'll dive straight into making a time crystal for ourselves using Qiskit.
Sorry to interrupt.
So before that,
Kartikeya,
many of you might wonder. Yeah, sure.
Sorry to interrupt. Can you go back to the previous slides? Yeah. Although I mean, I know this might require some more physics background, but can you at least try to intuitively teach us like what's the intuition that like time symmetry could be like
okay
breaking?
So So the second law of thermodynamics basically says that entropy tends to increase with time, right? That disorder increases. And time translational symmetry says that if I perform an experiment now, or at say 10 days later, I'd expect to get the same results, right? Now, breaking discrete time translational symmetry would be that I won't get the same results at any continuous point in time. I would only get the same results at certain discrete intervals. For example, at t is equal to 0 seconds, 1 second, 2 seconds, etc. But I won't get the same results at say 0.5 seconds. So that is what is known as breaking discrete time.
What should I imagine what will happen in like 0.5 seconds?
So that was the problem because of the second law of thermodynamics. If we break the discrete time translation symmetry, we are basically saying that the system is behaving periodically in time, right? It is going back to the same state that it was at t is equal to 0, at t is equal to 1. So the entropy isn't necessarily increasing. It might have increased at say t is equal to 0.5 seconds, but it decreased back to what it was at t is equal to 0 seconds. So that doesn't make sense according to the second law of thermodynamics. Yeah.
So should I think of the entropy actually stays the same, or is
no? What we were expecting it to be is that it increases at initially, let's say at t is equal to 0. It goes to a maximum and then decreases back to what it was before.
Okay. Yeah. You mean this is also predicted in time crystal, or it's like a...
Yes. We'll see that this actually happens in time crystals.
Okay.
Yeah.
So, maybe you can go ahead and I can.
Yeah, sure. So so what I was saying is that many of you might wonder, and researchers also stress upon this, that in principle, we can simulate time crystals on a physical classical computer. But the problem with that is that the bits in our computer, the classical bits, don't evolve in a way that looks like the physics we are interested in, though the numbers that come out from the calculations replicate the outcomes of the hypothetical experiment. On the other hand, on a quantum computer, the qubits themselves exhibit the discrete time crystal behavior. The qubits of a quantum computer, in a sense, become a discrete time crystal when we use this Qiskit to simulate time crystals on an IBM Cube computer, for let's say. So here is on the left-hand side is a complex-looking quantum circuit with an initial state, and we are performing some operations on it to formulate the time crystal for ourselves. We don't need to worry too much about the details here. The important thing here is the diagram on the right-hand side. So we have a parameter here that we can adjust given by G. When its values say 0.6, we have something which is known as the thermal phase. We can understand it like it is. Let's say we have an observable Z, it starts at some value 1, and with time it evolves, oscillates dynamically, and basically saturates to a constant value after some time. So this process is known as thermalization. But what happens if we change the parameter to say a higher value, say 0.97? The same observable shows a periodic nature with time. And it shows a periodic value. For example, if we sit anywhere in between this graph, say at t is equal to 25 seconds, the graph would look the same on either side. And this periodic graph is basically the proof of the formation of a time crystal. So many of you might wonder, why do I care? So what time crystals are? So the important thing, as I was just saying, is that it beats one of the classical physics most important laws, the second law of thermodynamics, which states that the amount of entropy or disorder always tends to increase and gives us the arrow of time and separates the past from the future, if we say. Also, these time crystals could help us make the quantum computers more robust, in the sense that they could serve as a memory in quantum computers, same equivalent to the silicon chips that we use on our classical computers. So this is almost it. To summarize, we learned about the Schrödinger equation, the quantum mechanics picture. We learned about how many body physics has different types of models. We learned about how to solve these models using processes like exact diagonalization and DMRG. And then it paved our way into the quantum computing regime. We learned why quantum computers are useful and how to simulate a discrete time crystal using Qiskit for ourselves. So this is it from my side. If anyone has any questions, I'd like to take up them now.
Yeah, maybe let's first thank Kartikeya. Yeah.
Thank you.
So, yeah, it's really great that we can have a more like a physics side perspective. Yeah. Yeah. And if anyone have questions, feel free to directly unmute yourself. Otherwise, I probably have lots of questions. Yeah, I want to ask, but I'll let people to ask first. Yeah, so if no, maybe let me first ask some questions about time crystal first, and then I have some general questions for condensed matter. So yeah, so maybe let me first rephrase my current understanding. Yeah, and maybe yeah, you can clarify. So it seems to me that time crystal is like a theoretical prediction in the beginning, like where like this guy who won Nobel Prize, like try to manipulate with some like I don't know, like Schrödinger's equation, etc., and try to like come up with some solutions such that the like there are some symmetry, but it's a discrete symmetry, like in the time domain inside the wave. Yeah, but then you say like okay, and people also kind of realize it. Yeah, but this also kind of break the second law of thermodynamics.
Yes.
Yeah. So then like how to think about it? So it's like I shouldn't think of thermodynamic like the second law holds in a quantum regime, or I mean, is this surprising to people or?
Yeah. So initially, like it was indeed surprising that it seemed that the second law of thermodynamics is being broken here, but it turns out that it is not actually. That the second law of thermodynamics operates at only the equilibrium only, right? It is very applicable to systems at equilibrium, right? But the system we are considering here is periodic in nature with time, like it constantly changes with time. So it is not never at equilibrium, to say. So what we observed here was this only. Yeah, here. So when we take G is equal to 0.6 and let it stay for a while, the Flockett system, the system we are considering, is not periodic in nature. So what happens then is that any observable quantity, it evolves dynamically and then saturates through a constant value. But when we change that parameter and our system becomes periodic in nature and not at equilibrium, the observable here shows a periodic nature in time, which demonstrates the proof of a time crystal.
Oh, I see.
Like
So
a time
maybe
we
I can.
imagined.
Yeah. I see. So maybe a way to think about time crystal is also like it is also a certain type of equilibrium, but rather than like just staying in one state, it is like
basically dynamic.
Periodic solutions.
Yes.
Okay. So then there's probably is potentially possible to have much more complicated time crystal. I mean, like more than two states, maybe multiple states, and even like some weird periodic structure could be possible.
Yeah, actually, it was first discovered by collaboration with Google, collaboration of Stanford with Google. The first time crystal was created on the Google quantum computer. The IBM people then also have simulated it using more dynamic systems. Instead of Flockett systems, they have also used systems like which don't necessarily evolve periodically. They change their parameters in a more random fashion. So there also, when we don't have an equilibrium there also we have seen the formation of time crystals. Like the necessary thing is that the system isn't in equilibrium. Because if it is, then the second law of thermodynamics is applicable there, and we will see the thermalization.
And also, I'm curious, like, so all, I mean, because currently now these are all like simulations, right?
Yes.
So so the first question would be like, do people try to really physically implement a time crystal? And maybe secondly is like, do people expect time crystal being something nature that you can maybe find somewhere in the universe? Or
so like finding a system in nature that is periodic in time and obeys many body localization is like not expected as much, but if we do, it certainly would form time crystal. And the second question is that people are trying to make time crystals more stable. Like the time crystals we are currently making, they have to be stabilized with constant inputs of energy. So people are wondering if we could make these time crystals more stable so that they can be used for as a memory device for quantum computers instead of the silicon chips that we use for the classical computers for ourselves. They are trying to make it a memory device, a permanent memory device.
Oh, I see. So you are saying there's still some external energy, like
yes. Because of the periodic nature of the system itself, it provides kicks, basically kicks of energy at certain times. So we are trying to see if we can make it stable.
The external energy is really required.
Yes.
I mean, like even in a theoretical model, I think.
Yeah.
Let's see. Well, thank you so much. Now I think I know time crystal slightly better. Yes. Yeah. Do people have more questions on time crystal? Otherwise, I actually want to ask a little bit about condensed matter in general. I think today you indeed already gave a quite good overview, but as an outsider, I'm still quite curious, like in general, like what's the direction of this field and what's the flavor of the frontier problems?
Okay, so condensed matter physics is basically trying to ask the ultimate question that condensed matter physics is trying to answer currently is specifically in the domain of non-equilibrium quantum dynamics. It is a subset of condensed matter physics. Just like we have a theory for equilibrium thermodynamics that we study in high school, etc. The things, macro observables like temperature, pressure, like things like that. We have proper laws for thermodynamics, the 4 laws of thermodynamics that we have. We are trying to formulate a similar theory for systems which are not in equilibrium. For example, the systems that we just saw that are used to make time crystals. We don't have any particular laws that govern them. We have certain hypotheses and things that govern them in a special condition, but we would like to make a general sort of thing, a general law that governs all systems, and specifically develop the field of quantum statistical physics, just like we have for the classical one. So that is the main goal of the condensed matter physics for now.
I see. And what do you think, or like what do the most people in the field think what's the main challenge? It's like those theoretical model being quite difficult to analyze.
Yeah, well, one of the main challenges is first of all is the simulating the larger system sizes, as we just saw. So and the second thing would be the incorporation of quantumness, if I say, in the classical simulations. Because the quantum computers that we have currently, for example, at Google or IBM or D-Wave and things like that, these quantum computers are not very stable. They have, because of the noise and error mitigation and things like, they are not very stable and are not the best places to simulate our quantum systems and to perform solid research. And on the other hand, simulating quantum computers on a classical system doesn't make much sense in the longer run, because we cannot incorporate all the properties like interference and entanglement and everything onto the classical computer. So the main focus is trying to formulate algorithms and to make hardware that helps us to simulate these condensed matter physics models on the quantum computer.
I see. And when you say like building hardware, is you building quantum hardware, right?
Yes. So to make them more stable.
Gotcha. Okay. Yeah, so maybe let's thanks Kartikeya again for the amazing talk. Yeah.
Thank you.
Thank you so much. And maybe I'll stop the recording now.